Yes, hello together to our statistics lecture. What did we do last week? We talked about inequality matrix in general, and we introduced the so-called concentration ratio, a very simple measure for inequality. Then we talked about the so-called Herfindahl index, which is widely applied in economics, and because actually it is some kind of a natural weighting what we are doing. If you remember that the Herfindahl index is just the sum of the squared market shares, then this squared, I say therefore that it is quite natural, since we use quite often, if you think for instance on variance, also about the squared distances quite often if we look on the dispersion or in the at the volatility of random distribution. And then we started with a larger topic in the kind of inequality measure, where we introduced the so-called Lorentz curve, where we compare the straight line between 0 and 1, which represents the uniform distribution, and then the wider we find the Lorentz curve on the right downside compared to the straight line between 0 and 1, the more unequal is our distribution. Oops. And this we did with some examples of distributions, and especially I think it was this one here, when the total market size is accumulated just at one firm, here at firm number 5, then you have this extreme case that the Lorentz curve is 0 and then just jumps up from the last part in the distribution to our 1. And well, this is only a visual representation of unequalness of a distribution, and then we started to introduce the so-called Gini coefficient, and this Gini coefficient was then defined just as the ratio of the area between the uniform distribution and the Lorentz curve. Area between uniform distribution and the Lorentz curve, and the triangle, this area just represents the extreme case of the most unequal distribution. area of the most unequal distribution. Well, and then we can show that this Gini coefficient can be calculated due to these two formulas, and this we will show in an exercise. And then we just calculated these Gini coefficient here. Oops. And to close this part of the lecture, I want also to introduce another last inequality measure. There are even more inequality measures, but I think concentration ratio, Lorentz curve, Gini coefficient, and now the so-called tile index, these are and Herfindahl index, of course, these are the most common measures if you want to have a measure for inequality within a random distribution. Well, again, it is something similar to our Lorentz curve or Gini coefficient or even the Herfindahl index. If you look at the definition, then at first we calculate the ratio of our random variable, for instance, the individual income. So this is an example, individual income relative to the average income. Or you can say it is the individual market size of some firm divided by the average market size of a firm, or individual market size divided by average market size. Well, and this is multiplied, maybe a bit surprising, with the natural log of this ratio. And why is this a measure for the dispersion or for inequality in our distribution? Well, this, of course, this number represents somehow the inequality, but why do we calculate this also with the natural log? Well, the idea multiplying this with the natural logarithm is that this connects then our measure with somehow a general understanding of disorder in our sample, because this can be interpreted as the entropy of our distance of the population away from the ideal egalitarian, and egalitarian would be then again our uniform distribution. This comes also from the information theory, where you also ask the question, how disordered is your information you have. And this is in general calculated via the natural logarithm. This comes also, this interpretation from physics, where you have some system and you ask for the disorder of this system. So this natural log comes from information theory or physics as a measure of disorder or entropy. And I think the word entropy you have also already heard. So to speak, we ask how disordered is our universe, for example, and that we become more disordered and disordered and disordered, and this then means that the entropy is increasing. So in this case, we know that the natural log of of 1 is 0, and then of course these numbers here can also be negative, and this then means that if we have a negative number here, we have negative entropy, that this then indicates that we quite far away from the ideal egalitarian distribution. So the uniform distribution would be then associated with the tile index equal to 0, and the maximum inequality we just would have again that the tile index would be just equal to ln of the number of our of the size of our random sample, and this again means that, so to speak, we have only one large firm in our market, and the other are also always only very small. What is a nice property? We won't show this in this lecture, that we can decompose this tile index into subgroups. So if you have, for example, you look at the income distribution of a country, then you can calculate the total tile index of the income distribution, and then you can, for example, look at the subgroup of the poor people, and within the poor people you have poorer people, or even the people who are worst off in your society, and a little bit richer people in this subgroup, and then you can calculate the tile index of the subgroup, and all tile indices then sum up to the total tile indices, and therefore, yeah, it is a quite good instrument in order to compare different subgroups within your distribution, while if you take the Gini coefficient, then you can only calculate the total unequalness of the whole distribution. And what we see also is, and therefore it is quite often used when you look at income inequalities, that it is really sensitive to redistributions from the very poor people to the rich people. Then you have a direct change in the number of your tile index, and Therefore, it is also quite often used in this kind of part of sciences when you are looking at inequalities. Okay, I think the Gini coefficients we had already. Or no, we have only calculated the here Gini coefficient of this distribution, but not of every examples. Okay, done. Let's start with the Gini coefficient of our different, no, this we had already, or no, this was the Lorentz curve. Lorentz curve, our distributions, and now I copied the wrong slides here, I think. Sorry. So dial index, this we have to cut, I think. So this one, this one, this one, this we had also already. This we don't need. And example A we had already. So this also, I think B, C, and D we didn't have. Okay. So in this case, then we start with example B in order to calculate the Gini coefficient. Or we see, oh, we had only shown the Lorentz curve. Okay, again, we have to calculate our numbers Fi and Gi, and let's do this again in Excel. Statistics, lecture, and I think we had this here. Nope. Where's my file? Anyway, let's copy this. This would be then Gini B. Let's take our data. Well, actually, we don't have to calculate much in this case, because why? if you look at this distribution, what would be the Gini coefficient? Actually, we can directly give the result. Oops. Since I'm alone here, I always have to restart the beamer. So what kind of distribution do we have here? I have to wait until the beamer is on again, otherwise I don't see the Zoom meeting. Uniform, great. And the Gini coefficient of the uniform distribution. So this is GI FI 1, 1. Yes, of course. Because our Lorentz curve is just also the straight line, and then the area between the uniform distribution and the uniform distribution itself is, of course, 0. I don't think that we have really to calculate this, or let's just do it. So we have 1/5, 2/5, 3/5, 4/5, and of course here we have the same. And the Gini coefficient is then of course 0. Then example C. I think then I can copy this from here. Yep. So what do we have to do then? In this case, we have, of course, the very unequal distribution. So what would be, in which neighborhood would be the Gini coefficient? Not exactly, but in which neighborhood would end up this Gini coefficient without calculating it. So we have 5 enterprises in our market, and we should have only one really large firm in this market, and all the other should be very small, or in our special example, they should have a market size of more or less 0. Then, what is the interval? The Gini coefficient lies in between. So GG is element of course, on the one part 0, and on the other side 1, of course. And if we have the most unequal distribution, then we are, of course, at the other extreme point So this should be then in the neighborhood of 1. And let's go into our, oh, you don't see it. I have to put it like this, then you see it. So here we have first copy. This would be then C. And we have 0, 0, 0, 0, and we have 1000 here. Then let's that you can see it. What do we need for calculating it then exactly? Of course, let's do it because in the next example we need this. Go to our formula. We have it here. So what we need the differences between Fi, and we need the sum of the Gi. So delta Fi and sum Gi. So here we need this minus this, and here we need the sum, so plus this, and very surprising, we obtain then the Gini coefficient as, first we need of course the sums here, is no, at first we need the product of both. This is A and this is B, and then we have A times B, and we obtain and then 1 minus A sum of A times B, and then we need here the sum. In this extreme case, it's of course only 0.2, but in the next example we need this, and GC is then 1 minus this, and this is then our result. So we end up here with exactly sorry, this was not wrong, right? fi minus ci. Not only 0.2, no, this is right, okay. And 0.8. And example D. Where do we have it? This one. So now we have up to 10. Example B. Okay, sorry. Yep. This one, and then we need just all these formulas here. Let's copy this and let's move to B. Or even I think it's easier, I just copy this whole and we only change the data. So, and then let's cut this. We move in here and we obtain B. And now we need here 200 for all 5 firms, and then of course we obtain our Gini coefficient of C. Okay? Well, actually we can also copy this one and put it on the slide. So a bit larger. Even more. So this is then 0.1.5. I need 2. So we can do this, I think. Oh, not working. So, up. Yeah, this is working. Why is this tool not working? No. Now it's working. Okay. And no. So it's not working, but I can do this, 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 and Now I can move this up here and now it looks better. Okay, this was B. And then let's put also example C in here. Yep. This would be C. And oh, this has to be here such a way. But you obtain the Excel file too. So then we go to our last one, the example D. And in this case, we have to move this a bit down. 2, 3, 4, 5, I think up to here. And we need now our 10. And put it like this. This. Need the sum again. And this sum is now to 13. Should be 1000 again. Nice. Down here. And now you see everything. Okay. So then we need our Fi. This has to be 0. This divided by 1000. This again we have to fix by the dollar signs and move this down to 10, and that you can see it, we need more digits. And this were the market sizes, and then we need our GIs. Oops. Oh, sorry. These are our GIs. So up. It's now happening. And cut this, and this should work here. No. Then again, let's do it, and this one, and no, this doesn't work. Why not? Oh, I know it. Because the other formulas on the right side then won't function anymore. Then again, divided by market size. And more digits. And here, of course, only 1 over 10. And now this is still not right. Because the GIs have to be the accumulated ones, and therefore have to accumulate this. So sum of this up to this, and the 3 we have to fix. Down. But didn't it add up to 1? I'm a bit... Oh, this one. 1 up, and the last one. Then we have our 1, and now we have our G's. But the Lorentz curve is coming from the data up to 13. So today we have a kind of an Excel curse. Let's move this down here. This we can move downwards. And this has to be the total sum until 13. And then we have our Gini coefficient of 0.38. So what we have done here is, of course, we start with our numbers FIGI, then we calculate always the difference between these FIGI. We calculate the sum of the GIs, multiply this, is this correct? Yeah. And then summing up all these multiplications of A and B, and then 1 minus the sum ends up with the Gini coefficient of 0.38. So in this case, then you obtain GC equals 0.38. And well, we could have done this, of course, also quite faster, since we know that here the first 5 single firms are at have the market size 30, and then we have 3 with the same size 150, and the largest firms with 200. So we can, of course, then also calculate this here. We have 5 times we have 3 times, and here we have 2 times. So Fi here would be then what? The relative number of 5 firms relative to 10 is then of course 0.5. The next one, accumulated plus 3 firms relative to 10, then we have 8 firms, so it's 0.8. And our GIs, I just have to calculate 5 times 30 relative to 1000, so I obtain here 0.15. Then I have 3 firms with market size 150. This is of course then a total market size of 0.45 accumulated with 0.15 is then of course 0.6. And then let's do this now by hand and not with Excel. Then of course we have F1 minus F0 times G1 plus G2. There we have done 0.5 times 0.15. F2 minus F1 times G2 plus G1 is then 0.8 minus 0.5 is of course 0.3 times this plus this is 0.75, and let's take another color. 1 minus G3 minus plus G2 is 1 minus 0.8 is 0.2 times 1 plus 0.6 is 1.6. So, and then we have this is, I think, 0.075. Hopefully I'm right. This would be 0.225, and I do it in my head. Hopefully I'm right. And this would be 160 divided by 5 is 32, 0.32, I think. And if we sum up all this 0.75, so this together is 0.3, and then this and this together is 0.62, and then we have 1 minus 0.62 is fortunately 0.38, which we have also here. So, of course, we can always do it also by hand, but if you think of a bit more data than 10 data points, then it is quite messy to do this by hand. Okay. What else? we have introduced our tile index, and therefore I also want with you to calculate the tile index for our distributions. So calculate the tile index for distributions A to D. Well, tile index for example B, and we have also to use A. Where's A? This is B, and here we have A. Then let's go here. So for this we had also the Gini coefficient, I think, and this was here also 0.8. And now here we want to have the tile index. Let's do this in red. But let's start with the tile index of example B. Why do I choose example B? Well, again, this is the uniform distribution. And if we go back in our definition of the tile index, then of course we have ln of xi over ln u, and of the by the uniform distribution, what is the average size of our firm? If every firm has the same size, then the average size is just the size of every firm. And then I divide here the same numbers, so I have a 1, and ln of 1 is 0, and therefore the tile index is also 0, and I do not have really to calculate anything. So in this case, here we have also tile index equals, oh, not here, but here, tile index equals to 0. But then let's take this one and let's do this again in Excel. There I can choose again to copy this one. Tile index A. This we don't need. This we also do not need. This we don't need, and we need the other market sizes. this one. And what do we need? We need, of course, at first the average of our, so x bar, and this is using the formulas just. The medium value, so the average size is 200, and then we need always, so this is our mu, I defined this, and then we need here xi over mu, so our 70 divided by 200, again we have to fix it, put it down here, and let's take a bit more digits. And we need the natural log, ln of xi over mu. So the natural log of this number here, also all 5 numbers, also more digits. And then we have, if we call this a and b again, we need again a times b. So multiply this one times this one downward, and in the end we need the sum equals this, and I think we have to divide it by n, or am I right? Yes, so we also have to divide it by the number of our firms. So then tile index will be this divided by 5, and we have 0.13. Let's copy this and put it into our slides. This was B, and then we take A, and this would be then the calculation, and up we have, oh, why it's not working? Now it's working. 0.13, roughly 0.14. So then we had here uniform distribution, of course, is just 0, and the Gini coefficient was here in the neighborhood of 1, and the tile index there we have learned that this is not in the neighborhood of 1, but if we have a really unequal distribution, then we should be in the neighborhood of, or it should be ln of n, So in this case, we just can calculate that this is ln of 5. So let's just calculate this. This one and copy. This would be C. And then we have 0. And the last one 1000. And of course, in this case, since the log of ln of 0 is not defined, we have to make an assumption that we define, in this case, if the log is not defined, that we just calculate 0. And therefore, we just set here 0. And then we see, of course, that we have this one and this one. Market size is then the log of ln of 5, because the 8 over the 10, and this one is not right. Dividing by 5, we end up at the log of 5, 1.61 equals 1.61, and also put this into our slides that you have it here. And this is a bit too messy, so take a new slide and let's take the numbers. And the last we want to calculate here, tile index. Again, we switch to Excel. This one, copy at the end. Number D, this, again this, and this one. Up. This has to be moved downwards. Let's take the data again. And we need now the sum up to 13. The average also up to 13. this down to 13, this down, the product of both, the sum up to 13, and now divided by 10. So also 13, and we have a tile index of roughly 0.28. Roughly 0.28, and the calculation we have here. Okay, and of course what you see here is that you of course can shorten your calculation if you again realize that you have here 5 times the same firms, here 3 times and 2 times, then of course you can also calculate 5 times this, 3 times this, and 2 times this, and then sum up. And then you will be quite faster. If you do it by hand, well, if you choose some software package, then of course it doesn't matter if you just put in this data or if you put in the aggregated data. Okay, then to end this topic in the lecture, I also want to show you some data of the income distribution in Germany. So if we look at the development of the Gini coefficient in international perspective, then you see more or less that we have here Germany has a relatively low Gini coefficient. So here we are, and roughly we are together with France, we have the lowest Gini coefficient in Europe. So Germany and France have relatively equal income distributions. So the Gini is calculated on income data. And well, what is maybe not very surprising is that the United States compared to the European countries are much more unequal in their income distribution. So Germany, they have roughly 0.3, while the United States have a Gini of 0.4. But well, how good is our calculation here? And there we have to admit that these calculations are based on official data. So everybody, also you, can go to the statistics office, and then you can get data on the income distribution of Germany. But what can you think of what data you don't obtain if you ask for incomes, especially? Well, especially you don't get data, of course, of the very, very rich persons. But you don't get data of very rich persons. Because, of course, you don't find them in some official um, data package. And for this, I looked up a little bit, and I found here a paper of Bartels and Jedanai on 2015, and they calculated implicitly how much income of the total income of Germany have the very, very rich people. And they calculated this from public finance data, from text data. So there you can then implicitly deduce how rich is a guy. And here, what is maybe not that surprising is that if you take the top promille of the German society, so the 0.1% richest people in Germany, they have roughly 4% of the total income of Germany. Or if you go even to the super rich people in Germany, then they deduced here that 0.01% richest people in Germany. So what does it mean? We have 80 million people in Germany divided by 100%, 0.1, another 0, 0.1, another 0. So what does this mean for Germany? This and this. So these are the 800 richest people in Germany, and what's their share on our total income. So our total income is roughly GDP, 3.5 billion euros. So they have 2% of our total income, total GDP, and these are all our billionaires in Germany. Well, and this part of the distribution is not included in this Gini coefficient of 0.3 for Germany. And if you add this data, then you see for this year 2015, we don't have other data for this, that then this was the Lorenz curve from official data. And if you take these top richest people in Germany, then this Gini coefficient really moves outside. And if you then estimate the Gini coefficient for Germany, you come up from a number around 0.3 to a number of 0.35. And I think this is actually, for me, it was quite astonishing this to find that just because of roughly the 1,000 richest people in Germany, you really have a huge step in inequality in Germany. And since this is an advanced course in statistics, this you always should keep in mind how good is your data. And if you write afterwards a bachelor's thesis or something like this, then and you want to do some quantitative analysis, then also always write some sentences about the quality of your data and what your data can say. Okay, then we have ended our topic about inequality, and the next time we will start with price statistics.